So last time I introduced you to the oscillator circuit, the simple BJT-based astable multivibrator. It has two states, this transistor conducting as a low-side switch with this on, this is your load, and this off, or the other way, this transistor on as a low-side switch with this load on and this load off. These resistors are as small as possible to be as unobtrusive to the circuit as possible, and these resistor-capacitor pairs are the RC networks that time the circuit. For a nice even oscillation, since we're not really trying to get PWM with variable duty cycle out of this, you're going to want identical resistor values and identical capacitor values. They don't have to be, but there's no reason you wouldn't. And it's a positive feedback circuit where this transistor conducting or not conducting determines how this charges or discharges, which feeds into this transistor, feeds into this capacitor, and back. And that's how the oscillation works. So if I were to give a simple diagram of the operation of this circuit, it has these two states. Let's call them 1 and 2. That doesn't matter, I'm just labeling them for a moment. These are the two well-behaved states. We don't say stable because it's an astable multivibrator. It's not going to sit in any one of the states, but it's going to gravitate towards one, and then the other, and then the other, and then the other. It's well-behaved because it's going to assume one of these two alternating, but it's not going to be like, okay, now we're over here, and over here, and over here, and over here. It's not a random behavior. It's a well-behaved, steady behavior that you can count on. It goes back and forth between the two. Now, when you first start the circuit, it could be unpowered. Let's say this is the completely unpowered state. Put a little dot. None of the transistors have anything going through them. They're nice and cooled down. Capacitors are fully discharged. Power hasn't been connected for years. It's just a cold circuit. Or you could have just unplugged the power and the thing is just starting to power down now. Capacitors still have charge and you're about to plug it back in. Or you could have just ripped out this capacitor and put another one in its place. So everything else in the circuit is winding down a little bit and then charging back up, whereas this one is fresh, or any number of other states. And apparently I have made a very happy Pac-Man ghost. But this is the trouble I've had, and I've gone to forums and everything else, and the best consensus I can get from everyone, including experts in the field, not directly talking to me, I'm not important enough to have experts talking to me, but reading what they've wrote. As much as I wanted to be able to describe how you get from an indeterminate state into one of these well-behaved states, the answer is there's 18 bajillion different variables. There's slight temperature variations, constructions of the parts, one charged, one uncharged, and you're going to get a different behavior each time. And while you might be able to use a simulator and set exactly a certain starting state and explain it from there, which is what I was trying to do, that's not useful, as it turns out, because that's one out of an indefinite number of states, and it doesn't really tell you anything about the circuit. So, for example, from a cold start, you can see positive is connected through here, so this transistor is on. Positive is connected through here, so this transistor is on, because they're both grounded. Base to emitter are both on. So this capacitor, if we use our Kirchhoff's voltage law, the voltage on this side of the capacitor is the junction voltage drop base to emitter here. And then over here, the transistor collector to emitter junction is open, but from a cold start, it has about the same drop, like 0.6, 0.7 or so, drop over the collector to emitter, despite the fact that it is fully conducting. So this capacitor isn't even charging, but then microseconds later, as this transistor warms up, so to speak, really gets going, the collector to emitter starts dropping down to where it should be. And this side drops, and this is charging. Same here, this is charging. So you've got both of these charging backwards in a different direction than they ever will in the stable setup. And both of these are on at the same time. And in principle, it would just stalemate there, but very tiny differences will just kind of kick it eventually. One of these will conduct better than the other one. One of these will charge faster than the other one or charge more than the other one by nanopico or less farads. Something somewhere is going to be just different enough that it's going to start wiggling and eventually wiggle itself into one of these two states. And that's why the circuit works, because it's going to wiggle, over microseconds, maybe even milliseconds if it's particularly degenerate. But once you get it going, it's going to get in this cycle, and it's going to stay in that cycle thereafter. So we're just going to forget about all of this. There's no good way I can explain it other than eventually it will end up in one of these two states. So no more crying over spilt milk. Let's go ahead and actually describe those two states. So I'm going to pick one, and I'm going to say, okay, let's assume this is what the circuit is doing. So that could be state 1. And then I will show you how it gets into state 2, and then I'll show you how state 2 gets back to state 1. So then we're not assuming anymore. As long as we know it gets into one of those two, and it does, then we've shown that it will go in that cycle. So let's assume the following. This capacitor is charging. This transistor is not conducting. So this end of the capacitor is connected to, let's say, 5 volts, because I like 5 volts. This transistor is conducting. So this end is connected to the voltage drop across the base to emitter junction, so 0.6 or 0.7 or so. So it's charging that way. So we have a positive charge on this end and a negative charge on this end, from the point of view of the capacitor, of course. There's no negative voltage here, but it's essentially the positive and negative end. Capacitors act like power sources, like your battery. The same way, if you have a battery or any power source and you're doing your Kirchhoff's thing, if you go from negative to positive of the power source, that's a voltage rise, because the positive is the conventional current output. The same way, if you have a capacitor. If you have a positive charge here and a negative charge here, and you go from negative to positive across the capacitor at a particular moment in time, using Kirchhoff's voltage law as a snapshot. So whatever the charge is, if you go from negative to positive, it's a voltage rise. At that moment in time, it acts as a power source. So in this case, if we do the voltage law this way, then we have a power source this way. Because just like a battery, here's the positive end. That's the output. So it's pushing that way. But of course, this is pushing harder, which is why it's charging. So that's how a capacitor works with Kirchhoff's voltage law. It's just the same as a battery or any other DC power source. You treat it exactly the same. If there's no charge, then it's a 0 volt power source, also known as a wire. So anyway, this capacitor is charging. This transistor is conducting. This transistor is not. Now, this capacitor also has the same charge as this one. See, it's symmetrical. So from the outside, positive is on the outside. So this one has the same kind of charge here. It was charging through here just like this one was charging through here, but it's discharging. And this is where I hand waved last time and said that this is choking off this transistor, that's why it's closed. So let's actually do the voltage law. This is the state. Capacitor charging, capacitor discharging, transistor on, transistor off. This is one of the states. So this transistor, low side switch, letting that through, this one blocked. So let's think about this. So if we look here, we start 5 volts, then we subtract whatever the voltage is across this resistor. We don't know what it is yet. Then we go here. This transistor is closed, so it's not there. So then we go across this capacitor, but we're going backwards. We're going from positive to negative. So we're getting a voltage drop because, see, this power source is pushing out its positive end, and that's the direction we're going. We're following the push. This capacitor is pushing out its positive end. We're going against it. So this power source is trying to push current this way. This capacitor is trying to push current back the other way. So we have our positive 5 volts minus whatever, minus the capacitor, and then over here, since this is forward biased, it's minus the base to emitter 0.6, 0.7 down to 0. So let me back up again. We've got 5 volts minus whatever volts minus this tiny bit equals this resistor. So you can tell this resistor is going to have less of a voltage drop over it. So there's no contradictions here. The capacitor will be charged to less than or equal to this power. The resistor is just taking up the slack, and so you can see why we have leftover voltage to allow this here. So we can use this loop, plus 5 volts minus whatever, minus the same 0.6, 0.7 to here. This is why this voltage is high enough to forward bias this junction and turn this transistor on, because the power supply and the capacitor are opposing each other. Think of it this way. The power supply and capacitor are opposing each other. The resistor is going to take whatever's left. That's the scavenger at the end. So these two oppose each other. Whatever's left, take out of that this. Whatever's left, this one will just pick it up. It doesn't care. It's taking the leftovers when everybody else has taken their slice. So we know this is positive 5 volts. This is positive less than 5 volts. So we know there's enough slice left for this. On the other hand, we look at this loop. So let's start here. Plus 5 volts minus whatever, and then we go this way, but we're going from negative to positive, right? We're doing this loop. Before, we're doing this loop through there, through the load, through the capacitor, backwards, and through there. But now we're doing the other current path through the same transistor. So we've got plus 5 volts minus whatever. Then the capacitor, we're going negative to positive in the direction it's pushing. See? This one's pushing this way. This one's pushing this way. They're pushing together the way we're drawing the loop. So it's 5 volts minus whatever plus whatever. And then the collector to emitter is negligible, 0.06 volts maybe, or less, and out to 0. So guaranteed 5 volts. And then this is greater than 5 volts. So this resistor is having to drop 5 volts here, whatever volts here, and then this is the only other drop, minus the wires, of course. And this drop is negligible, so we ignore it. So the resistor is pretty much the only actual drop in this part. So what happens is you've got 5 and you've got something that's greater than 0, which adds up to something that's greater than 5. So this resistor has a voltage drop that's greater than 5 if this is 1 volt. So we've got plus 5, then we've got plus 1, and then don't worry about this. So this has to be minus 6. Plus 5 plus 1 minus 6. But we're tracing. So if we start here, measuring relative to ground, we're going to see plus 5. And here we're going to see minus 1, because this has 1. So it's plus 1 when we go across the capacitor, but we haven't done that yet. Plus 5 minus 1, 0, because we just got plus 1. See? Once again, plus 5 equals 5, minus 6 equals minus 1, plus 1 equals 0. That's effectively 0, down to 0. So we have a negative voltage here at this spot while this is discharging this way. And it chokes off because you've got -1 at the base and 0 at the emitter, so it's reverse biasing the NPN junction, see? PN, base is P, emitter is N. If we treat that as a diode, which it's not a diode, but if we treat it as a diode, it's like this. It expects a higher voltage here than here, but we're giving it 0 here and -1 here. So the voltage is trying to go backwards, and it won't allow it, unless it gets so high that you break your diode. And this is a concern with the circuit. In my Googling, it was mentioned that your transistors have to be able to handle the negative power supply across the base to emitter junction, because it's going to be negative. In fact, your negative power supply plus this, just for safety. And plenty of transistors handle that just fine. You just have to look at your spec sheet and make sure it can handle that negative voltage. But that's how the circuit works. When this capacitor is discharging, it ends up sucking this down to a negative voltage because this resistor has to compensate for the power and the capacitor working together. They're both pushing in the same direction, so the resistor has to catch everything else. If you had a load down here, something else dropping the voltage, that wouldn't be the case, because this would drop some and this would drop some, and this wouldn't have to bring it down to negative there. You could have plus 5 here, and then maybe this only drops 3 volts, so now you're at plus 2, and this has its 1, so now you're at plus 3 again, and then this could drop 3 volts and be down to 0, or something like that. But we don't have a load, we have an insignificant voltage drop. So this is choked off, which is causing this to stay high. This is not choked off, so it's allowing this to be low. This is charging, this is discharging. This is one of the states. Now, we've assumed that we got into this state. This is all assumed. I've explained what's going on, but we're assuming we got here. So now let's stop assuming and say from here. Well, eventually this capacitor is going to discharge down far enough to be 0. So it's going to stop discharging. It's going to reach 0 because you've got positive connected here with negligible here, and then you've got, because this is conducting, you've got 0 here with negligible here, so you're effectively getting the whole voltage. So it'll go down to 0, which is not going to help here, because again, this loop, you still end up with 0, so that's still not going to be forward biased. But then it's going to start charging this way, because before you had this, and it was discharging out the positive end, and then you run out. It's empty, and it starts charging the other way, and you end up with a positive charge here and a negative charge here, because the whole reason it was discharging is you had a positive charge here and a negative charge here, or rather a positive voltage here and a negative voltage here opposing the charges, so it was able to dump its positive into the low voltage and its negative into the high voltage. So you've still got the high on the left and the low on the right, and it starts charging in the opposite direction until this voltage at this spot gets up to the voltage needed here to turn this on. We do our Kirchhoffs again. plus 5 volts, minus whatever, but now we're going positive to negative. So now it's just like over here. See, because we had the power supply pushing this way and then the capacitor pushing against it. Now we have the same thing. The power supply is pushing in, the capacitor is charging, and it's now pushing against the power supply. So this is opposing the power supply voltage, essentially, in this loop, because this is still on. Everything's still normal. The only thing is different is this is charging the other way. So now the capacitor is starting to oppose this power, which means the voltage drop across the resistor goes down. The resistor has to drop less, because this is a drop now. So this is dropping some, this is dropping the rest. The more this drops, the less this has to drop, which means at this spot, it's going up. You can look at it as this dropping less, so you're less negative there, or more positive. You could view this as this side of the capacitor is charged positive, whichever way makes more sense in your head, that's fine. But the thing is, this is now dropping some, so this is dropping less. So when we do our loop, we go plus 5 minus 4, because this might have 1 volt, let's say. It's not going to, it's going to have 0.6 or 0.7, but let's say it has 1 volt. So you do plus 5, but then it goes down to 1. This is only dropping 4 volts because as soon as you cross the capacitor, now it's down to 0. Plus this, minus this, going from positive to negative, negligible to 0. So this is going to charge that way until it gets just high enough to turn this on, 0.6, 0.7 volts or so. So now we're in the transition. Now we're no longer in that nice, stable, well-behaved state, rather. This is just turned on. It's barely turned on, but it's turned on. So guess what? This negative is now leaking through. This loop now exists, and we can say positive 5 or whatever, minus whatever from this load. But down here, we're going to have a rapidly dropping to negligible collected to emitter, because it's not there yet, but it's rapidly shrinking down to the minimal amount it will be, just like it is over here. So now this is conducting down to 0. So going backwards, we have 0, negligible, so effectively 0, where there's positive. So this one immediately starts discharging. And then over here, we have a familiar loop. We have a power supply, a resistor, and then a charged capacitor, and we're going negative to positive. And then negligible down to 0. So we have this power supply and this power supply both pushing in the same direction, so this resistor is having to drop both. So you might have plus 5 here, plus 4 here, minus 9 here, but at this point it would be 5 minus 9 is minus 4, and then this plus 4 brings it down to 0. So you'll have negative 4 here. All of a sudden, you have negative 4 at the base, 0 at the emitter. That's choked off. That's how it gets choked off. This starts discharging, and this resistor ends up causing a massive negative voltage here, which this transistor has to survive. So this is no longer conducting. So here, this now no longer exists. So now you have your high voltage here, where the negative is, and then this is conducting. So you've got plus 5 minus whatever, minus 0.6 or 0.7 down to 0. So this voltage is going to be about 0.6 or 0.7. So you've got a high on the right, low on the left, opposing this. So instead of charging, it immediately discharges. It had only gotten to about 0.6 or 0.7, turned this on, and then both transistors flipped, and it's immediately discharging back to 0. So it only reverse charged about 0.6 or 0.7, which is why electrolytics are fine, because it's only going to charge reverse up to 1 base to emitter voltage drop, and then it'll flip and heal the oxide again. So it discharges down to 0 once again. And then, since this is still happening, this one's still discharging. So this is still a negative voltage, so this is still off. It starts charging. We've got our high voltage here, our low voltage here. So about 5 here, about 0.6, 0.7 here, because this load is not conducting through there. So we end up with building a positive charge here and a negative charge here, like we were thinking. And now we have suddenly reached the other state. So now we have one capacitor discharging, the other one capacitor charging, the other one transistor conducting, the other one transistor not conducting, the other one. These 4 components have reversed, and this load is now passing through the transistor, and this load is not. So then the reverse happens. Eventually this will discharge down to 0, which is going to put 0 here, which is still off for this, and then, see, it had reached 0. So this one's still charging merrily away with very little current. It's going to, as more of the capacitor is charged, as the capacitor is charged more, it opposes the current, so the load is getting less and less and less until it gets effectively none. So now the capacitor starts charging, and it starts getting the positive over here and the negative over here. So the positive here, see, it starts opposing this power. This is pushing this way, this is pushing this way. The resistor is dropping less and less until it reaches what this needs to turn on. This will turn on. this will start discharging. That'll choke off this, which will make this one discharge back to 0 from 0.6 or 0.7 and then start charging. And that's us going back and forth and back and forth. So that's really the key to take away from all of this. That's the one linchpin, is this choking off effect. When you have a charged capacitor discharging through a transistor, you're going in the direction of the power and in the direction of the power, and there's basically nothing there to worry about. So the resistor has to drop both cooperating pushes. So you end up with a negative here because you're going to get to 0 here, but you're not there yet. That's the key. Now, if this was still not a clear enough explanation, I would appreciate comments, and I can always make another video in the future with further details answering people's questions. Right now, I'm in a weird state where I understand it, at least as far as I can tell, and I'm trying to explain it to you as I've learned it, but I might be skipping over some things because I've been studying this for a week and change at this point. So there's some things I might be just taking for granted. So please do tell me. There are simulators out there that will give you graphs or even a visual representation with dots representing current. Just look for Astable Multivibrator simulator or something similar, and they'll give you different types of explanations, but I thought the Kirchhoff's voltage law explanation would be the most useful. It seems to be for me, because simulators are great, but this way, using the voltage law on piece by piece by piece, I feel like it helps me understand the pieces more. If I want to see how an entire circuit behaves, the simulator's great. And if you want to test a design, like using Spice or something, that's a program that gives you fancy graphs, that's what you use when you want to have a complex circuit and simulate it and make sure that you're not wasting money sending your design over to China to have it fabricated. For understanding electronics at a fundamental level, I honestly believe going back to Kirchhoff is the easiest way. The math is simple. It's just addition, subtraction, multiplication. In fact, for Kirchhoff's voltage and current laws directly applied, it's just addition and subtraction. The multiplication just comes in when you're trying to figure out what the voltage drop over a resistor is from the current. When you're trying to do a full circuit analysis using the voltage and current laws, but we don't even need that here. We don't even need that here. We can use just the voltage law. We don't need the current law because we're only analyzing individual loops. And voltage law is easy. For a power source, increase the voltage if you're going negative to positive. Decrease it if it's going positive to negative. So from negative to positive is a voltage rise. Positive to negative is a voltage drop from the way you're drawing the loop. Because remember, you can draw the loop however you want. The math will work out as long as you maintain your signs. For a resistor, it's always going to be a voltage drop in the direction of the current. So you have to know which way the current flows. That's usually easy. If you're opposing the current while you're drawing the loop, it's a voltage gain. In the direction of the current, it's a voltage drop. Capacitor, it's a power source. Same way. Negative to positive, voltage gain. Positive to negative, voltage drop. If it's not charged, it's just a wire. It's the same thing. It's a 0 voltage drop. Transistor or diode, junction. If it's conducting, if it's forward biased, then you have a fixed drop. If it's not forward biased, it's an open circuit, it's not there. Treat it as if the wire's not there. The collector to emitter junction, you can calculate the current from your beta or whatever, but it's the same thing. If it's conducting, then collector to emitter is going to be roughly nothing. Don't worry about it. If it's not conducting, it's an open circuit, doesn't exist. That's it. You just take a snapshot in time and trace whatever you want. So like I said, tell me if you'd like any more clarification on any aspect. But right now, I'm going to go back to circuit development, because there's only a couple more videos until we have our working DC to AC converter, and then we can move on to the next project. So until then, be seeing you.